Hi, I am Sanjay Patel. In this video, we are going to discuss nth derivative of two special functions. One is y is equal to x plus square root of x square minus 1 raised to m, and the other is y is equal to x plus square root of x square plus 1 whole raised to m using the Leibnitz theorem. And we'll see that there are many other problems which can be solved with the help of these two. And they are all interesting ones. In our previous video, we have discussed three problems on Leibniz theorem, based on Leibniz theorem. And now let us go to the next one. So I'm starting with the problem number, say 4. Okay. So if y is equal to x plus square root of x square minus 1 raised to m, then prove that x square minus 1 times yn plus 2 x square minus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0 for every n. Every n belongs to m. So let us prove this relation, and for that we'll apply the Leibniz theorem. So the solution of this. So this is a very important problem. You must keep in mind we are going to solve many interesting problems using this one. So if you can understand how to prove this, you can have the solution of many other problems. So let us start with the given function. Here y is equal to x plus square root of x square minus 1 raised to m. Okay, that is given. Differentiate this with respect to x on both the sides. So the first derivative we get is y1, and here something raised to m, you can write its derivative as m into something raised to m minus 1 first. Okay, and then the derivative of this bracket quantity, that is this derivative of this thing, is given by into 1, derivative of x is 1, and derivative of square root of x square minus 1 is 1 upon 2 root of x square minus 1 into derivative of x square minus 1. This x square minus 1 is 2x. So this is the first derivative of the given function. Let us simplify this. So on simplifying, we get y1 is equal to m into x plus square root of x square minus 1 raised to m minus 1 into here these two will be cancelled. The LCM of this two terms is x square root of x square minus 1. So what I will get here is square root of x square minus 1 into 1 plus x. So this term is this expression is same as this one. We can multiply these two, and let us write this square root of x square minus 1 on the left hand side. So multiplying both the side by square root of x square minus 1. What we get next is this thing. So this implies square root of x square minus 1 into y1, I am taking this term on this left hand side, is equal to m times x plus square root of x square minus 1. It is a raised to m minus 1 into a. So final product will be a raised to m using the power indices rules. Okay, but this thing x plus square root of x square minus 1 raised to m is nothing but our function y, which is given. So I can replace this bracket on the right hand side by y. So that gives me square root of x square minus 1 into y1 is equal to m times y. Now to go further, let us square both the sides. So we will get x square minus 1 into y1 square is equal to m square into y square. Okay. Now again differentiate this with respect to x on both the sides. So differentiate with respect to x on both the sides. Okay. So differentiating this, we can write the derivative of the left hand side here as using the product of u into v rule, that one can take this as u, other as v. So first of all, x square minus 1 as it is, derivative of y1 square is 2 into y1 and derivative of y1 is y2 plus y1 square we can keep as it is, and derivative of x square minus 1 we can write as 2 into x. And on the right hand side we have m square into y square. M square is a constant, so it is as this. Derivative of y square is 2y and derivative of y is y1. Now you see in this we have y1 rather 2 is common everywhere on both the sides, and y1 is also common. So I can cancel that 2y1 and write this last step as x square minus 1 into y2, because this 2y1, this 1y1 and 2 here, and this 2y1 will be cancelled. So plus x into y1 is equal to m square into y, and that implies we'll get x square minus 1 into y2 plus x into y1 minus m square into y is equal to 0. So this is the relation between y, y1 and y2. Now we'll take the nth derivative of this on both the sides. So let us write in the next step, taking nth derivative on both the sides, we get nth derivative of the first term. I will write like this: x square minus 1 times y2, its nth derivative, plus nth derivative of x into y1, and here m square is constant, so that minus m square remains as it is, and nth derivative of y we can write directly as yn is equal to 0. And for these two we can apply the Leibnitz theorem, because they are the nth derivative product of two functions. So let me write this way. This is one function, this is another function, and in Leibniz theorem, you know, the function whose derivative becomes 0 after a certain stage, that we take as v, and x square minus 1 is a polynomial of degree 2, so third derivative will be 0, so I am taking this as v and the other function as u. So this implies applying the Leibniz theorem for the first bracket, we will get nc0 and say derivative of un, that is yn plus 2, derivative of y2, nth derivative of y2 is yn plus 2, into derivative of the function x square minus 1 as it is, plus nc1, then 1 less than this, that is yn plus 1, into derivative of this, first derivative of v, that is v1 according to the Leibniz theorem, 2x, plus nc2 yn into 2, and then other terms will be 0 because the next derivative of this constant will be 0, plus this thing, again we have to apply nth derivative rule of Leibniz theorem for these two. So this I am taking as v and this as u, okay, and writing nc0 NC 0, and nth derivative of u, that is y1, is yn plus 1, and v function, that is x as it is, plus nc1 yn, 1 less than this, and derivative of x is 1. So we stop here because the next derivative of 1 will be 0, so all other terms are 0. And the last term, let me write in the new line, minus m square into yn is equal to 0. Now let us simplify this. So this implies nc 0, that is 1, so yn plus 2 into x square minus 1 into x square minus 1, okay, plus for this nc1 is n into 2x, so 2nx into yn plus 1. Here nc2 is n into n minus 1 by 2 factorial, so that will be cancelled with these two. So I am writing directly n into n minus 1 into yn, plus for the second bracket nc0 is 1 into yn plus 1 into x. So it is x times yn plus 1, and for the last term here it is nc1, that is n into yn, and plus this one, that is minus m square into yn is equal to 0. Okay, now simplifying again, so x square minus 1 into yn plus 2, and let us collect the terms containing yn plus 1. One is here and other is here. So what is common in this? 2nx plus 2nx, and x is here. So x into yn plus 1 is common. So I can write as 2n plus 1 into x into yn plus 1, and plus for the remaining terms containing yn, there are 3 terms containing yn. So here I can write n square minus n. If you simplify, then this is plus n, and for the last term we'll get minus m square, and taking yn common from all this. Okay, so this gives us x square minus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0. So because these two will be cancelled, and this was the required result. You can see here x square minus 1 into yn plus 2, 2n plus 1 times x into yn plus 1, and plus n square minus m square into y. So that is proved here. Now let us go to the next problem. Okay, number 5. So problem number 5. If y is equal to, let me say, if y raised to 1 upon m plus y raised to minus 1 upon m is equal to 2x, then prove that, the same thing. So let me just copy and paste this. So then prove that. Okay, so we have to show this thing. Let us solve this problem. It looks say a new problem, but we can transform into the previous one. So let us start with the given function or a relation here. Y raised to 1 upon m plus y raised to minus 1 upon m is equal to 2x. Just for simplicity, let us take say y raised to 1 upon m is equal to t. Let us put a substitution for this. So what I will get here is t raised to m, t only, plus y raised to minus 1 upon m, you can write as 1 upon t, because y raised to 1 upon m is t, so y raised to minus 1 upon m is t raised to minus 1, that is 1 upon t, and is equal to 2x. Okay, so we get this. And let us simplify this. So we'll get t square plus 1 is equal to 2xt. You can multiply both the sides by t, so we'll get this. Now taking this 2xt on the left hand side, we can rewrite this as t square minus 2xt plus 1 is equal to 0. I would like to make this into a perfect square. So let us add and subtract the x square, because I can make these two terms into perfect square by adding x square. So I will write t square minus 2xt plus x square, and then subtract x square also, plus 1 as it is equal to 0. Okay, so this implies if you correct these two terms, you will get t minus x whole square, and taking these two terms on the other side, we'll get x square minus 1. So this implies we'll get t minus x. Okay, let me write bracket here. So t minus x, taking square root on both the sides, will take positive square root. Even if you take negative square root, you will get the same result. So let me write square root of x square minus 1. So taking square root on both the sides, so taking positive square root. Yeah. So this gives me t is equal to x plus square root of x square minus 1. But what is t? T is y raised to 1 upon m. So I'm putting the value of t now. So what I will get is y raised to 1 upon m. Y raised to 1 upon m is equal to x plus square root of x square minus 1. Okay. Okay, because t is equal to y raised to 1 upon m. Now taking nth power on both the sides, we get y is equal to x plus square root of x square minus 1 whole raised to m. What we have done is we have taken an mth power on both the sides. Okay. Now you note that this function is same as the previous problem, in which we are given y is equal to x plus square root of x square minus 1 raised to m. Then its nth derivative is this. So it is already proved. Just you have to write this complete solution of this problem after the last step in the next one. Okay. So we don't need to prove this. What we have done is we have converted this problem into the previous problem. So just as in problem number 4, okay. So this implies I'm writing directly the nth derivative we can write as, by the problem number 4, we can get the last step as x square minus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0. Okay. Now the next problem. So every time we need to prove only or convert only into the problem number 4 for the problems which I am discussing here. So next is problem number 6. If x is equal to cosec 2 theta, x is equal to cosec 2 theta, and y is equal to 10 raised to m theta. Okay, then prove that uh, the same thing in the previous problem. Then prove that x square minus 1 into yn plus 2 plus 2n plus 1 into x. So this proof will also use the problem number 5 solution. Here the function is given in the parametric form. Okay, they can use the derivative of parametric functions and then find dy by dx, or you can use any other method. What I am going to do here is I will remove this parameter or eliminate this parameter theta and obtain a function y of x. So let us start with this. Here we have x is equal to cosec 2 theta and y is equal to 10 raised to m theta. Okay, this I can write as x is equal to 1 upon sine 2 theta. Okay, and this I can write as y raised to 1 upon m is equal to 10 theta. Taking 1 upon mth root on both the sides, I will get y raised to 1 upon m is equal to 10 theta. Okay, and just for simplicity, let us call this as say t. This is equal to say t, and now for this x is equal to 1 upon sine 2 theta, I will use the formula of sine 2 theta in terms of tan theta. All you know is sine 2 theta is 2 tan theta upon 1 plus tan square theta. So I can write this as 1 plus tan square theta upon 2 into tan theta, because sine 2 theta formula is 2 tan theta upon 1 plus tan square theta. Now we can substitute the value of tan theta, that is t here, and t is actually this thing, y raised to 1 upon m. So this implies we get x is equal to 1 plus t square upon 2 into t. And let us simplify this. So what I will get here is, this implies 1 plus t square is equal to 2xt, which we can rewrite as t square plus 2xt plus 1. Okay, and this is equal to, sorry, this is not plus 2xt, it is minus 2xt is equal to 0. And again, as in the previous case, we'll convert this into perfect square. So t square minus 2xt, and let us add and subtract x square, this plus 1 as it is. So this will give you t minus x whole square is equal to x square plus 1. And taking positive square root on both the sides, we get t minus x is equal to square root of x square plus 1. And that gives me t is equal to x plus square root of x square minus 1. And this implies, what is t? T was y raised to 1 upon m. So y raised to 1 upon m is equal to x plus square root of x square minus 1, because t is equal to y raised to 1 upon m. And now you can see immediately that this becomes our problem number 4 only. So y is equal to x plus square root of x square minus 1 if you take mth power on both the sides. Okay, if we take nth power on both the sides. So now we can write this is same as problem number 4. So the solution is already there. It is the same thing. Using this, we can prove that x square minus 1 into yn plus 2. We have already discussed the solution. So this problem is also solved. Okay. there is another problem which can be converted into problem number 4. So let us solve that also. So number 7, problem number 7. If say x is equal to 1 by 2 times tan theta plus cot theta and y is equal to 10 raised to m theta, then prove that the same thing, prove that x square minus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 and so on. Okay, let us solve this also. So we'll see how to convert this again into problem number 4. Here we have parametric equations of the function x is equal to 1 upon 2 into tan theta plus cot theta and y is equal to 10 raised to m theta. Okay. So this I can write as x is equal to 1 upon 2 times tan theta plus 1 upon tan theta, and this I can write as y raised to 1 upon m is equal to tan theta, and let us call this as t. Okay, and putting the value of tan theta is equal to t in this, what we'll get is x, rather let us write 2x here, 2x is equal to t plus 1 upon t, because t is equal to tan theta, and that gives us 2xt is equal to t square plus 1, multiplying both the sides by t. Okay, and this gives us t square minus 2xt plus 1 is equal to 0. So again, as in the previous problem, this we can also make into the perfect square by adding and subtracting x square. So t square minus 2xt plus x square, okay, minus x square plus 1 is equal to 0, which gives us t minus x whole square is equal to x square minus 1. And taking the positive square root, we get t minus x is equal to square root of x square minus 1, and therefore t is equal to x plus square root of x square minus 1. Again, that t was y raised to 1 upon m, so I can write y raised to 1 upon m is equal to x plus square root of x square minus 1, and now taking mth power on both the sides, we can write this as y is equal to x raised to, y is equal to x plus square root of x square minus 1 whole raised to m, taking mth power on both the sides. So again, this is transforming into the problem number 4, which is same as problem number 4. Okay, and there is one more type. See, even if you have minus sign over here, this reduces to the same, and that I want to explain in our next problem, that is problem number 8. Okay, if y is equal to x minus square root of x square minus 1 raised to m, okay, then prove that, okay, see, this is, let us solve this one, number 8. Okay, here we have y is equal to x minus square root of x square minus 1 raised to m. Okay, so taking the first derivative, we get y1 is equal to say m into x minus square root of x square minus 1 raised to m minus 1 into derivative of x plus square root of x square minus 1 is 1 minus 1 upon 2 root of x square minus 1 into 2x. Okay. We want to prove this relation, so we'll obtain the relation between y1 and y2. Simplifying, we'll get y1 is equal to m into x minus square root of x square minus 1 raised to m minus 1 into square root of x square minus 1, okay, square root of x square minus 1, and this is minus x. These two will be cancelled upon square root of x square minus 1. Okay. This implies what I will get here is square root of x square minus 1 into y1 is equal to m into x plus, m into x minus square root of x square minus 1 raised to m minus 1. And from this numerator, I can take minus 1 common and write here. And this you can write as x minus square root of x square minus 1. So simplifying, what you will get is square root of x square minus 1 into y1 is equal to minus m times x minus square root of x square minus 1 raised to m. This term is nothing but y. See, this is the y. So we can substitute y in place of this, and what I will get here is square root of x square minus 1 times y1 is equal to minus m into y. Now squaring both the sides, we get x square minus 1 into y1 square is equal to m square into y square. Okay, and this relation is exactly the same as the relation obtained in the first problem of this video, that is problem number 4. Let me show you. It is this thing here. It is this equation number 1. Okay, and our rest of the problem solution goes like this. So after this step, you must just write this same solution, and you will get the same final result, x square minus 1 yn plus 2, same as in this last problem. So let me write this way, which is same as same as 1 in problem number 4. So we have started with the problem of finding nth derivative using Leibnitz theorem of the function y is equal to x plus square root of x square minus 1 raised to m, and discuss problems related to this one. In the next lecture, we'll be starting with a similar function y is equal to x plus square root of x square plus 1, and find nth derivative of this and discuss problems related to this. So you'll get a set of different types of problems just using these two solutions. Okay, so that's all. Thank you.